Professor Pfitzner was a professor in the Department of Aerospace Sciences at Munich University of Germany, German Federal Armed Forces for 21 years before his retirement on January 1st, 2022. Professor Pfitzner received his PhD degree in physics from the Technical University of Munich. His research interests are broadly on the modeling of turbulent combustion, CFD simulation of high-pressure real gas reacting flows, transcritical phase decay, turbulent heat transfer, flame wall interaction, particle combustion, flows and rotating geometries, heat transfer in porous media. Professor Pfitzner was awarded the Best Paper Award in SME Turbo Expo in 2015, and he is also a reviewer for multiple journals such as Combustion and Flame, Combustion Theory and Modeling, International Journal of Heat and Mass Transfer. And the title of Professor Pfitzner's talk today is Large Eddy Simulations of Inert and Reacting Transcritical Real Gas Flows. If you have any questions during this talk, please submit them in the Zoom chat, and I will ask Professor Pfitzner at the end of the presentation on your behalf. Thank you. And the time is yours, Professor Pfitzner. Please share your screen and start your presentation.
Thank you very much.
Okay.
Dr. Xiangpeng.
Yeah, yes.
I will share my screen now.
Okay.
Okay. Let's see. Can you see my mouse?
Yes, very clear.
Okay, very good. So yeah, this talk will be on work we have done during the last about 10 years. We had a joint research collaboration with TU Munich and University of Stuttgart and the Technical Universities of Aachen and Braunschweig on rocket combustion. And our task in this project was the modeling of the combustion at high pressures in rocket combustion chambers. And out of this work, we developed the technique to do large eddy simulations of inert and reacting transcritical real gas flows. And we chose to use OpenFOAM for that task. Okay. Okay, I have to do this. So this work was done with several PhD students, Lena Jacek, Hagen Müller, Julian Zips, Christoph Taxinger, Matthias Bannholzer, Paula Breda, who are all now as PhDs. And the contents of the talk will be, after a short introduction, I will tell you a little bit about real gas flow physics. Some of this you may know, some of this may not be known so much to CFD persons. I will tell you how we introduced that in a pressure-based real gas code. Actually, when we started, all the other real gas codes were density-based, and we had to figure out how to do that in a pressure-based code. Then I will show you some validation of inert jets. And at the very end, I will talk a little bit how real gas can be implemented in the simulation of combusting flows, especially applied to non-premix flames, which is the usual case in combustion, in rocket combustion. So where does real gas effects occur in technical applications? As I said, it is really prevalent in rocket combustors. In such a big combustor, you have pressures which can exceed 100 bar, 200 bar in the modern ones. And you can see here the combustor of such a rocket combustor, and you can see here the injectors. These are very special injectors. In rocket combustors, you have so-called coaxial injector, where you have a center tube where the liquid oxygen is coming out, and then you have an annual tube where the fuel comes out in gaseous form, which is usually hydrogen or methane. And this is a view of the injector head of this Vulcan injector. This is actually 566 of these injectors. In the middle, you have the igniter. The other application which I will talk about is gas motors. So usually either in buses or in for generation of electrical energy, methane is also combusted in the form of internal combustion engines. And as we found out in the framework of a project, here also the regas effects tend to play a role. So first, I will concentrate on the rocket combustors. And here again, you see the injector and the combustor. And this is our simulation of the flame, which I will introduce later, where you can see it's very turbulent flame, and the colors here are the temperature. So you can see there's a large effect of subgrid turbulence here. But first of all, we have to deal with how to model this thing with these high pressures and the low temperatures, which are prevalent in these rocket combustors. So typically the oxygen is injected here at below 100 Kelvin, which is around -200 degrees Celsius, and it is actually in liquid form. But you have these high pressures, meaning that it is liquid, but as a liquid, it is supercritical. I come to that in a moment. And the modeling challenges in terms of CFD is that you have you have to implement an equation of state, which is not ideal gas. And you have, as a consequence of that, very high gradients of density in the fluid, which you usually only have if you have embedded shocks. But the structure of the flows is quite different. So if you just use numerics, which has been developed for shock capturing, this may not work. Because, for example, there's no pressure drop across these layers where large density gradients are in. And if you have a sensor which just looks at the pressure, it will not actually turn on. So, as probably all of you have learned in your thermodynamics lecture, if you look at the state diagram of a fluid, of a single component fluid, this is, I have here the pressure, this is the volume, and this is the temperature. Then this surface here represents the equation of state. And you can see this is here the liquid gas region. So as, for example, at constant pressure, you increase the temperature, you will first heat up the liquid, then some liquid gas mixture will form, and you will not increase the temperature as long as everything is, all the liquid is converted into gas, and then the gas will be heated again. And you can see if you now increase the pressure, so if I was going at this line here, above the critical pressure, you will not have a separation into liquid and gas. And this is the supercritical region here. So you can see, especially this diagram, which is the PT diagram. And you can see this is the evaporation line where above is the liquid, below is the vapor, and here is the supercritical region. You will see this. This is just the same plot, but logarithmic in pressure. And I will show this plot as a reminder later on. So this is the critical point, and at the temperature above the critical point or pressure above the critical point, you will not see phase separation. So now if we look at experiments which have been done at high pressure, looking at this transition here, I have selected 3 experiments done at Lampoltshausen, where they injected cryogenic nitrogen into hot nitrogen. And you can do this experiment basically at the pressure which is below the critical pressure. This is shown here on the left-hand side. So this is a line which sort of goes like that. And you can see at the boundary between the liquid nitrogen and the hot nitrogen, you can actually see droplets forming. So there's some surface tension. This is similar to a spray, but you also can see some Schlieren here. So something which does not look really like a spray. And you can, from the large difference in color, you can see that the density is very, very different here than it is here. I will show how larger that is, but you know, if you boil water, liquid water has a density of around 1,000 kilogram per cubic meter, whereas gases, water vapor at normal ambient pressure has a density which is around 1,000 times smaller. This is the difference is much less at these high pressures, which you can see here in this diagram. So if you boil at low pressures, you have a large increase in volume. If you boil at high pressures, there's only a smaller increase in volume, which means there's only a smaller decrease in density. Yeah, we come to that later. So now if I boil this thing at a pressure which is above critical, you can see there's no there are no droplets forming, and you can see these comb-like structures here, still very large difference in density. And if I go to a pressure which is almost 3 times as much as the critical pressure, so that would be up here somewhere, you can see this looks more like a dense gas mixed into a not so dense gas. And as we all know, the surface tension can only exist in a subcritical state. So how do we now model in a CFD code such an equation of state? What most people do is they use a so-called cubicle equation of state, which means that the pressure is not, you don't have the equation of state pressure times volume is equals to gas constant times T, but you modify the denominator here by some constant B, and then you have a term which is due to the intermolecular forces, and this is parabola in the volume. So if you calculate this, the pressure will be a third power polynomial in the volume. And this equation of state actually can reproduce the strong variation of density. And now we see here the typical density of nitrogen if you go for higher temperatures. So this is the critical temperature here, like 126 Kelvin. If you go for large temperatures, then this is the typical evolution of density with temperature, which is just 1 over temperature. So it's like a hyperbola. But then you can see as you get near to the critical temperature, there's a very strong rise in density, which is actually like a factor of 5 or 6 in this case. And if you want to, so the points are from the NIST database, and then if you want to simulate that, you can use the Peng-Robinson equation of state. You get this line here. So you can see the Peng-Robinson equation of state over predicts the density at low temperatures, and we have used a correction here. There has been so-called volume correction to this equation of state, where there are some additional terms, and this turned out to be able to reproduce this density very, very nicely. And you can also see that near the critical point, the specific heat is having a very high peak. And this has also to be calculated correctly if you want to have the heat transfer correct. Now I come to the validation of the implementations. So we used again this experiment where I showed the first experiments here. So this is again nitrogen from a central nozzle into a hot chamber. You can see the chamber temperature was the gas temperature in the chamber was like 300 Kelvin, and we have, among others, studied 2 test cases for the jet. One test case was with an inflow density of 400 kilogram per cubic meter. Test case 4 only had a density of 150 cubic meter, and the chamber density is something like 50 kilogram per cubic meter. We modeled that the chamber as a round chamber, and the injector flow was modeled like a fully developed turbulent tube flow by just simulating with LES a tube flow and feeding the exit into the inlet. You can see the computational grid for the large eddy simulation, and this is the result of case 3, case 4, and another case which is similar to case 3. So what you can see here is that although the inflow temperature of case 4 is only a few degrees higher than the inflow temperature of the case 3, the jets look completely different. So if you would analyze that with typical Reynolds analysis, the Reynolds number would be almost identical, and you would say the jets have to be almost similar, almost the same. But this is not the case, and the reason is that the density in case 3 is much higher. So for the surrounding nitrogen, it's much more difficult to actually wrinkle the shear layer. So the jet is much longer. Here the jet is much shorter. And there's actually from this experiment density measurements along the central line. And you can see here that the Raman measurements we could catch very nicely with this Arbor-Dur equation of state. We had a collaboration with the Technical University of Munich. They had a density-based code using the same thermodynamics, got very similar result. They had completely different numerics. They also had a different subgrid turbulence model, and still the good results we could only get if we here used a very accurate equation of state. This is not necessarily the case for other cases, for ideal gas jets, where subgrid the sort of subgrid turbulence model does matter. But here it turned out that thermodynamics was really the most important thing. And here you can see the density in case 4, and again we also match the density very, very nicely. So the accurate equation of state was validated. In this slide, I would like to tell you a little bit about the modification we had to make to the standard numerics of OpenFOAM for this pressure-based calculation of real gas flows. What we found is that the standard piezo loop, which is just iterating the pressure equation, generated large artificial pressure waves. So we got a lot of artificial disturbances, which made it very difficult to converge, or actually hindered us to get good results at all. And the reason was that if the pressure equation uses a constant temperature and constant, all the other quantities are constant here, if it comes back with a pressure which satisfies the continuity equation at a certain density field, and the density is so sensitive, so the density, if you are in this region here and the density is so sensitive to pressure and temperature, then when you go into the thermodynamics module and recalculate the density, the equation of the continuity equation will not be satisfied anymore. So this was the reason for these artificial pressure fluctuations, and we had to do actually two modifications. One modification was that we included the thermodynamics in the pressure equation, although that is expensive, but it turned out we had to recalculate the thermodynamics inside of the pressure loop to make sure that on exit from the pressure loop, the continuity equation is still satisfied. And the second observation was that the standard piezo loop holds the temperature constant. while the equations, the transport equations we are solving is an enthalpy equation. So basically, the set of equations is for density or for pressure, which is equivalent to density for the momentum and the enthalpy. But in the piezo loop, the temperature is held constant, and this is not consistent in the case of real gas. So basically, for an ideal gas, you might know that enthalpy is only a function of temperature. So whether you use enthalpy or temperature is not important. It is, if temperature is constant, so is enthalpy. But in real gas, this is not the case. So in real gas, we had to use the enthalpy equation included in the piezo loop and also use the thermodynamics all the time. And that turned out to make a very good job. The resulting algorithm is also more effective than a density-based one, because in a pressure-based formulation, you don't have to deal with the speed of sound restriction on the time step. So CFL number here could be calculated with the velocity and not with the speed of sound, which was making time steps much larger. So this was the validation with pure components, but in the real case, we have the liquid oxygen, which mixes with the fuel, which is methane or hydrogen. So we have to look into mixture of real gases, and this is actually more complicated than one might think, because now you have two fluids, both of which have such a diagram, but the different fluids have different critical points. So you have to really look into multi-component thermodynamics and how to model that. And if you look into the literature, you find that if you mix two fuels, which have different critical pressures and different critical temperatures, that the critical temperature of the mixture is usually something which interpolates the temperatures, the critical temperature of the mixtures. So here we have a hydrocarbon which has a critical temperature like 520 degrees Kelvin, and some nitrogen with 126. So the critical temperature of the mixture will be like that. But the interesting thing is that in mixtures, the critical pressure can be orders of magnitude higher for the mixture than for both components. And if you look now to a diagram, temperature versus mixture, then here you have the critical temperatures of the two components. If you now increase the pressure above the critical pressure of this component, then you see that the two-phase region, which is this thing here, it first detaches from the left from x equals to 0. And if you increase the pressure further, you can even have phase separation if the pressure is higher than both the critical pressures of the components. And this is a very interesting phenomenon which I got interested in, and I wanted to know how this happens actually in these mixtures. This can occur, for example, in diesel engines, where the pressure inside of the cylinder at the point of injection can be 2, 3, 4 times higher than the critical pressure of the diesel fuel. So the diesel fuel in its own vapor could not form droplets, but if you have air present, then actually droplets can form. And I will show some experiments and some simulation of that later on. So that is something interesting. I did not actually know this very well when we started the project, but yeah, we managed to model that. Now, if we apply this to the mixture hydrogen-oxygen, like we have in the rocket combustor, you can see here the same diagram like this here, where you have the temperature and you have the hydrogen mixture, and you can see if the pressure is just the critical pressure of the oxygen, which is 50 bar, then this is the two-phase region. And if you increase the pressure, say to 100 bar, then there's still a very large two-phase region where even at 200 bar, which is 4 times the pressure, the critical pressure of oxygen, there's still a large region where droplets can form. Now I show you how to model that. Actually, it turns out that in thermodynamics, there is a rule which is called the corresponding states. So you can describe the mixtures by the same form, by the same formal expression like a single component gas, but you have to calculate these constants here, A and B, as a function of the A's and B's of the components. So you just calculate these A's and B's, get the mixture ones, and then put them here, and then you can calculate at the corresponding mixture, you can calculate the pressure. And then you can also calculate the enthalpy from standard formalism, and you can validate the enthalpy as a function of the mixture content of nitrogen. You can see we get a good agreement with the NIST data, and also the Cp, which is basically the derivative of this enthalpy. Oh, sorry, this is density. The Cp, which is the derivative of enthalpy, is also showing this peak, which interestingly shifts as temperature is modified. So this is a good agreement here. And going back to this slide here, there is experiments of the two-phase region, which are these points, and then from the equation of state you can calculate what you would expect, and you can see there's quite a good agreement. So for thermodynamicists which are not interested in CFD, this would be considered not a very good agreement, but to get a much better agreement you would need much more expensive equation of states, which would be too expensive to use in CFD. So we were satisfied with that sort of agreement. And then we went on to calculate, again, validation experiments. And there is some interesting effect, real gas effect, which cannot happen in ideal gas mixtures, which I will now explain. So when you mix two components like hydrogen and nitrogen in a chamber at constant pressure, you will get a mixed state. And if you look to thermodynamics books in a process where pressure and temperature is held constant, the resulting enthalpy will be constant. Now the enthalpy in a real gas equation of states is a function of pressure and temperature. From this mixing, there are interesting effects which you cannot have in ideal gas mixtures. So if you have two ideal gases mixing, then the mixing temperature will always be between the temperatures of the two constituents. If you have a real gas, however, you have an enthalpy of mixing, and this, so it can be an endothermic or exothermic mixing process, and this causes the effect that the mixture temperature can actually be lower than the temperatures of the two components. Likewise, if you look at the densities, in ideal gas, the density of the mixture will always be lying between the densities of the two constituents at constant pressure. If you have real gas, the density of one component here, the hydrogen, can be higher than the density of the pure hydrogen. So that is something we can look at in the results. And now I show some validation we did on, again, DLR experiment with the same chamber, but now we have a central jet of nitrogen and a coaxial jet of hydrogen. And you can see that the case E4, the temperature of the nitrogen is subcritical, whereas in the case D4, this temperature of the nitrogen is supercritical. So here in the D4, the density is like we had before. The density is like this case 4, whereas in the case E4, the density is much higher. So what they did in this case is they adapted the velocity of the hydrogen such that the momentum ratio between the nitrogen and the hydrogen is the same. And you can see here the density, which is like 3 to 4 times higher in case E4 than D4. So now I show the results. Here is a little write-up of the grid. Again, basically the same grid as before. And you can see here the subgrid model is the Bremen model. It does not make so much difference in these jets where you don't have walls, but anyway, Bremen model. We also later on we usually use the Weyl model. And here you can see a movie of the mixing. This is the case with the lower density. You can see these Schlierens here. There's obviously this is a supercritical temperature, so there is no surface tension forming, and the Reynolds number seems to be relatively low. If you compare the case E4, you can see due to the higher velocity of the hydrogen here, we have much larger Reynolds number, we have a larger wrinkling of the surface. But interestingly, since the momentum ratio in both cases is the same, if I go back to D4, you can see that the length of the jet is rather the same. So that's interesting, and we can now compare the detailed data. But before we do that, we look at this effect. Can we have temperatures which are below the injection temperature? And we can see here these gray regions in case E4, where we have the lower temperature. Let's start this again. We can actually see regions of temperature which are below the injection temperature of the hydrogen. If you would see that in the ideal gas case, you would have to say, my numerics is not doing the right thing. I have undershots and overshots in the region of large density gradients. But here it's actually a physical effect. And what you can see also, if you now look at the temperatures within the mixture, for green is D4 and blue is the E4. If we calculate this adiabatic temperature, the adiabatic mixture, then we get these lines here. And we can see that the actual LES temperatures, they are bounded by this adiabatic mixture. So this is, but they are still near to it. The other thing which we can see from this diagram is that in case E4, this is the phase separation line, we would actually expect some droplets forming. And I will look into that as a next chapter. So in this case, we just did it as a post-processing. We said, okay, we have here two-phase effects, and we should model that. We could only do it here in post-processing, but this was the next point of study which we investigated. So the question is now, why do we see these higher temperatures than the adiabatic mixing line? And the reason is that we also have some heat conduction across the shear layer. So basically, after mixing, the hydrogen is much hotter than the nitrogen here in the center, and there's some radial heat conduction, and this heat conduction then leads to a heating up of the mixture. Okay, so that was the investigations of the Lambertshausen test cases with single component and double component mixtures, inert still. And the next experiment we did in the framework of this research the collaborative research initiative was to analyze an experiment which we prepared and analyzed together with the University of Stuttgart. So they did the experiment. Again, it's an injector into hot gas, but here it is, we chose N-hexane into nitrogen because there we could deliberately go into this two-phase region without cooling down. So in their chamber, they could not cool down the apparatus. They had to operate the apparatus at 300 Kelvin. We could only influence the temperature of the injected fluid, and my PhD student, Christoph Daxinger, then tried out different fluids, and he found that N-hexane would do a very good job. And I shown now for different injection temperatures the adiabatic mixing line. So here you can see the content of nitrogen versus temperature, and so the temperature of the chamber gas nitrogen is 300 Kelvin. And then you can, for 600 Kelvin injection temperature, you can see this line here. For 560 Kelvin, you can see this line, and for 480 Kelvin, you can see this line. What you can see here is, again, the two-phase region. And here we have a cutout of this showing that in case of the 560 injection temperature, we would sort of just barely graze the two-phase region here. The 600 Kelvin should not cut through the two-phase region, whereas the 480 line goes fully through it. So before the experiment, we were predicting that in the 600 Kelvin case, we should not see any droplets. In the 560 Kelvin case, we might see droplets, but in the 480 Kelvin case, we definitely should see droplets at supercritical pressure. You can see here the critical pressure of nitrogen is 34 bar, the critical pressure of hexane is 30 bar, the chamber pressure was 50 bar, yeah, and these were the inlet temperatures. So that were our predictions, and from this setup here, you can see the guys at Stuttgart, they had two measurement techniques. One is a light through, so they just installed a light source behind the chamber, and then they looked at the jet and basically saw the density, the big density of the jet as a shadow. The other measurement techniques was me-scattering, where you just shoot in light from the side, and then you look at 90 degrees, and if there is some droplets or some small particles in the flow, then you should see some light. So let's see the experiment now. On the left-hand side, you can see in the top half this shadow graph, where you basically can see the extent of the jet. And in the lower half, this is overlaid with color from the me-scattering. And if there's no color, then there should be no droplets. If there is some color, there can be some droplets. And if there is a yellow color, then there should be droplets. So, and you can see this is the simulation here. As expected, the 600 Kelvin case should not have any droplets. The 560 case should have some. You can see the scale is very small here, should have some droplets. And then we have the 480 case where everything should be full of droplets. And you can actually see in the 480 case, the droplets are actually visible in the image here. And in the 560 case, you can see no droplets in the picture, but you can see some scattering from the me-scattering. So the theory is fully confirmed. And also the jet angle here is very well reproduced by the simulation. So that was very nice because we predicted before the experiment was done, and it was fully as theory predicted. The next thing we looked at in another project was injection in these internal combustion engine motors. Here methane is injected at very high pressure, usually 300 bar or even 600 bar, which is highly supercritical regarding the critical pressure of methane, but the temperature is usually like 300 Kelvin. At the beginning of the project, we looked what would be the effect of that. So we can see that the speed of sound actually is a lot different if you include real gas effects in the equation of state. Actually, speed of sound is like two times what you would expect from ideal gas calculation. Density is not so much different here in this case, but the CP again is like factor 2 to 3 higher. So if you consider that, now I want to show this, if you consider that through such a nozzle with very high pressure difference or pressure ratio, you have a supersonic jet, then in the nozzle you'll have Mach equals to 1. And if you calculate the speed of sound by a factor of 2 wrong, then the mass flow will be off by a factor of 2. This can be quite interesting if you try to design such a system. So here we have the challenges. Now we have a supersonic jet with the rocket combustors. It's very low, Mach number like 0.1, 0.2. Here it's supersonic, and you have these shock structures, these shock cells forming. So now we needed a numeric which can cope with very strong shocks, with large shock trains. And here you already can see the numerical Schlieren from our calculation and experimental ones for, this is, I think, a nitrogen jet. You can see that numerics works very well here. So what did we do here? For Mach numbers smaller than 0.1, 0.3, sorry, we used the piezo formulation which I showed. And for Mach numbers larger than 1, we switched into a compressible scheme, which was developed by Kurganov-Tadmor and which was generalized to real gas states by Krapushin and my PhD student Van Holzer. So this is a very interesting scheme which I encourage to try. And this hybrid solver then was used in a runs mode to calculate experiments which were done in this case by ETH Zurich, by the group of Professor Boulochos. So the solver was validated, the numerics of the solver was validated with this with two problems which are usually used for compressible solvers. One is just a nozzle with critical nozzle here, and you can see that nozzle is a shock is forming in this region, and you can see analytical solution and the numerical solution which worked very well, and also the SOT problem where you have a tube, constant diameter with a diaphragm separating high pressure and high temperature from low pressure and low temperature, and then you have a flow which has a shock and an expansion wave and a conduct discontinuity which you can only see in the density. You can't see it in the pressure. And you can see that again, the numerics works very well for this unsteady problem. And we also looked into that in real gas case. You can do a Riemann solver for the real case as well. And this also works very well. So this is experiments from injections from this nozzle here into 300 Kelvin chamber, and you can see the jet shape, and you can see the jet penetration depth as a function of time, and the nomenclature, this numbering here says the pressure is, the inlet pressure is 300 bar. The injector pressure, and the pressure of the chamber is here. So 60 means 60 bar in the chamber, 30 bar, 20 bar, 15, and so on. And you can see from the experiment, these are the dashed curves. This cutoff here is because the window was restricting the field of view, and we could actually very nicely reproduce the injection depth of the jet. And this was another very nice result when we now switched on this two-phase phase separation routine, we found that when we inject 300 bar methane into 60 bar chamber, we would not have any phase separation. But if we lower the chamber pressure, then we should have phase separation inside of the shock cells. And when we lower the chamber pressure further, then the two-phase region and also the shock train should become longer. And you can see on the right-hand side, this was again a real prediction from the code showing where should we see two-phase separation. It is Mies scattering. And on the left-hand side, these are the experiments from the ETH Zurich, and you can see it is almost identical results. So again, very nice, shows that thermodynamics is always working usually fine. So that is now the last part of my presentation. The goal basically was to simulate supercritical combustion in, so that means you have a LOX jet now and you have a surrounding hydrogen or methane, and you want to simulate these flames taking into account real gas. So now the question is, where do we expect real gas effects? How much does it affect the mixing and so on? We decided as a combustion model here, we also did other things, but in this presentation, I show you how to set up a flamelet model with real gas effects. So now combustion people know that if we assume unity Lewis numbers, we can introduce a mixture fraction and we can solve the flamelet equations, which are basically simulating the mixing between oxidizer and fuel flow. And now we increase the pressure and use our solver to solve the combusting flow or the flamelet equations using real gas. One interesting thing from thermodynamics is if you calculate the total enthalpy, you can see that the total enthalpy is not changed during combustion as long as you assume unitary Lewis numbers and as long as you assume no radiation loss and no heat loss to the walls. So total enthalpy will be constant, and it will be a linear function of mixture fraction. And this is also true in real gas. So we can use this as a calibration of our calculation. The thing is that now pressure and temperature will depend non-linearly on the enthalpy. But the total enthalpy is still linear. And now you can see what comes out of the real gas flamelet calculations. You can see that, note that the mixture fraction scale here is logarithmic. You can see that the density in the cold mixing region is increasing very highly because of low temperatures, but then it is very similar to the ideal gas case where it should be, and the temperature also is very similar to an ideal gas calculation. So we noted that there is a little difference here between the temperatures from the real gas calculation where it should actually be ideal gas, and we found that the reason why the temperature is not exactly approaching the ideal gas case was that at the inlet, here at the fuel inlet, where we set the temperature, the enthalpy in the real gas case is different from the enthalpy in the ideal gas case. So actually, when we did the calculation using the ideal gas state at the inlet, we made an error in the enthalpy, and we corrected that. And then my PhD student Zips, he devised this solution strategy to calculate a real gas flamelet using only ideal gas solvers. So what he did, he solved ideal gas flamelets. This then makes an error in the density and a slight error in the temperature. Then he calculates the real gas enthalpy, and he uses real gas thermodynamics to using the ideal gas mass fractions to calculate the correct temperature and the correct density. And then he does the PDF integration already, which then goes into the CFD code. Now in the CFD code, interestingly, you can actually ignore the big real gas effects. You can use the density and the temperature directly from the PDF tables. So basically, you can use your normal CFD code, and the real gas effects will just go through the flamelet tables, which now contain the real gas effects. And remember that only the density couples into the momentum and the continuity equation. So it is important that you get the density right, but the density will only be different in the region where the mixing occurs. Okay, so you can see that this worked very well in the calculation. Now you can see that the model reproduces the real gas flamelet calculation with the full thermodynamics. And the last thing I show is the validation. This is an experiment which has been done at Onara in France. And what they have is a typical coaxial injector now with liquid oxygen and gaseous methane around it. Here we have a chamber pressure of 56 bar and the temperature of the oxygen, which is 85 Kelvin. And you can see the light scattering from the flame. Here is the experiment. You can see there is this flame, which is like a mushroom a little bit. And this was actually very difficult to reproduce. In our first approaches without the correct real gas thermodynamics, we always had too long flames. And also with Run's models, it did not work. But in the end, when we used a good LES and we used a good thermodynamics, we got this very nice result here. What you also can see is that the density has very strong gradients here. The temperature is very turbulent, as we can see. And this was actually the picture at the very beginning, which I showed, where you had this very nice structure. And you can also see the compressibility factor, which is 1 when you have ideal gas, and you can see that the compressibility factor is quite different from 1 if you go here into the jet. And you have also very strong gradients. So that's my conclusions. At least for rocket combustors and for also for diesel engines and gas engines, you should take into account the real gas effects. The strong density gradients require modification in the numerics, and what is done for shock capturing is not always working. We developed among the first groups in the world a pressure-based real gas CFD code, and we applied that as runs and LES, where we needed a hybrid compressible formulation for the high Mach number flows. We showed that cubicle ERS is not bad. It's even better if you use volume translation. Okay, and then if you want to simulate these multi-component flows, you really have to use multi-component thermodynamics, which is not very difficult to implement, but yeah, it's just important to know that even at supercritical pressures, you can have phase separation. Okay, and the last thing was that if it's a diffusion flame, you can actually use flamelet tables, and you don't have to have a real gas flamelet solver, and you don't have necessarily to have a real gas CFD solver to calculate such flames. And that's it. Real gas CFD is often exciting and surprising, and whoever is interested, I recommend to try it out. Thank you very much.
Thank you, Professor Pfitzner. Thank you for the very wonderful talk. And now I will go through the questions asked by the audience. And now I only have one question. For the other audience, you can still submit your questions in the chat. Okay, the first question is from Professor Wei Yao. How did you calculate the sonic speed of two-phase mixture? This is important for supersonic flow.
Let me look into the chat.
Okay.
The sonic speed, yeah. Actually, the sonic speed can be calculated. There's a correlation which is quite accurate. But usually we calculate the sonic speed from the equation of state using directly the derivatives. So you can, in a two-phase mixture, you can calculate this from the thermodynamics. And the interesting thing is that in the two-phase region, usually the sonic speed, the equation, it drops down a lot from the sonic speeds of the two components. So you can have the effect that in a nozzle you have blocking of the sonic blocking of the nozzle if there's some two-phase mixture in the narrowest throat, just because the speed of sound is dropping down so much. So I don't have a foil here, but it's in our papers how we do that, and it's also compared to the correlation, which is often used to calculate the speed of sound.
Okay, thank you. Next question is from Professor Huang Wei Zhang. Thanks, Professor Pfitzner, for the informative talk. How can a phase change be predicted under such high pressure conditions? Thank you.
Okay, there I actually have a foil. So what you do is, this is described in thermodynamics books. You have to find the minimum of the Gibbs energy in this state. So the Gibbs energy as a function of components at a certain pressure and temperature is a complicated function, but it can be calculated from the equation of state. And then you can see this is such a shape if you cut it through, and you have to find the state which has the lowest Gibbs energy. And if this state corresponds to gases or liquid state, then there's no phase separation. But if it corresponds to a state where there's phase separation, then you will have phase separation. This is actually a quite complicated method. It is standard in thermodynamics books, but it took my PhD student Christoph Traxinger more than half a year to put it into CFD. So it is described in our papers, and it is this tangent plane distance method of Michelson. And there's papers of Fickel, Matthijs, and Traxinger which describes that in detail. But it's actually, if you want to do that inside of your CFD code, it is not easy to make robust, and it is taking a lot of time. So usually what you do is you first make an estimate in a cell. Is there a possibility to have phase separation? And only if there's a possibility you would calculate this flash. And then out comes basically the fraction of liquid and gas.
Okay, thank you, Professor Pfitzner.
Okay, next question is from Professor Zhi Chen. Thank you, Professor. It was a fantastic talk. How did you model the two-phase flow and OpenFOAM? Was a volume of fluid method used?
No, we are not using volume of fluid here, but we are using an additional transport equation for the fraction of the two phases. So if you remember, my slide here. So where is it? Here, you can see this beta parameter, and the beta parameter says how much liquid we have in the mixture. So it's like a mixture fraction, but it says how much liquid in the liquid gas mixture. And there's an additional transport equation for that. So we know there is, for example, 30% of liquid in the mixture, but we are not resolving phase boundaries. One could do that, but it is actually not necessarily easy, because if you look at these droplets in the experiment, they could not even with microscope resolve the droplets. They may be very, very small, like nanometer size. So it would be very difficult to resolve the very small droplets at the beginning with volume of fluid methods. But other groups have used volume of fluid methods. For example, if you look at the beginning of the jet, where the liquid jet comes into the domain, there very quickly there would be some some surface tension forming, and this could be calculated with volume of fluid methods. And you can still use the full real gas thermodynamics inside the jet and outside the jet. You can also, there are methods to calculate the surface tension with real gas effects.
Thank you, Professor Pfitzner. I have two questions myself. The first question is, in your simulation of the jet flow, besides the real gas effect, how do you consider the multi-component diffusion of different species for the gas?
Well, that is, you can, as long as you have no phase separation, then you can actually use if you would do something like a DNS, you would just you could just diffuse the different gases with a multi-component diffusion algorithm. So assume we have a DNS where we resolve everything and everything is in gaseous state. Then you can just put in, like Hertzirvis showed us his differential diffusion algorithm. And in each cell, you would have a certain mixture of your components, and you can throw your multi-component thermodynamics on. So that would be straightforward. If you think of a LES of a runs, then it is more difficult, because then you have the turbulent diffusion and you have the laminar diffusion, and the question is, will you actually see effects of differential diffusion still on a LES or on a run cell level?
Okay.
Now, so if the laminar diffusion is much smaller than the turbulent one, then the differential diffusion effects will not be visible actually.
Thank you. And the next question is, how much more time is needed for the calculation of real gas effect and the LES calculation? Is the method robust or not?
That depends on the case. If you have a single component or two components, then it's like 50% more if it's efficiently implemented. As long as you don't do the two-phase calculation. So this flash, if you do the flash, then it can easily be 3 times the time you need for a normal LES simulation. So basically, the implementation of a cubic equation of state is not very expensive. What is expensive is these other things, calculation of derived quantities like speed of sound and such things. But like the experience is like 50% more execution time for if no phase separation is involved. Okay. The other thing to be remembered is that you do have in these rocket combustors, you do have these shear layers which have extremely high density gradients. So that means you have, for numerical reasons, you have to put a very fine grid to resolve these gradients a little bit. Otherwise, there will be a lot of numerical problems. And if you have these very fine cells and you do LES, then the time step may become very small. But this is something you have to live with. This is.
I understand. Okay, Professor Boson Wang has one question he will ask by himself.
Hi, Professor Pfitzner. Thank you for your talk. As we know, the supercritical or transcritical fluids and combustion is very complicated. A lot of phenomena is involved. What I know is maybe following the question of Chenji. I mean, supercritical combustion, maybe it seems simple, easy for me because there is only one state, and we need to model the state, the gas phase, the state equation, and to calculate the thermodynamics. But it is if in the transcritical state, usually we have one phase in the subcritical phase, and one is in the supercritical phase. And in addition, we will have an interface. The interface usually is secant. And if we have phase change, the interface should have how to say, it become vanished and then appear. It's a dynamic. But during my investigation to see, usually we only see people doing simulations like using one state of equation or calculate the volume fraction. Usually neglect the surface tension force and usually neglect the effect of the interface, and also neglect the maybe the complicated phase change and the dynamic process. So can you give a judgment how much effect is it? Do we need to make it deeper investigation to see more detailed process, or maybe from a practical point of view, this is not necessary, and because we have seen good results from your investigations? Yeah, thank you.
Actually, I think you have to judge your question in terms of what you are interested in. So if you, as I said, if you were interested in more from a theoretical point of view in the jet breakup, like you wanted to do a DNS with volume of fluid method, then you would have to implement the surface tension, and then it's except that you have to implement the thermodynamics, most of the numerical effort would go into this detailed DNS-like simulation of the jet breakup. So that would be complicated, and you could probably only look at the very first regions of the breakup. If you were interested in a spray, in a liquid spray, then we could look at this simulation here, where you just solve an additional equation for the liquid to gas ratio. So in that respect, this would be very similar to a simulation where you simulated a spray breakup. So I think this is not so expensive, basically. So the other question you, I think, mentioned was how would you deal with the surface tension vanishing? But I think this is if you were in the realm of volume of fluid method, then this should not be such a big problem. So if in the volume of fluid method you are not really as a sharp interface resolving the interface, but you're smearing it anyway. And if the surface tension along the calculation vanishes, then you are back to just mixing. I'm not expert in volume of fluids, but I would assume that the volume of fluid just works if you set the surface tension to 0. Does that answer the question halfway?
Yes,
Yeah.
I think I have gained some information from your discussion. Yeah, thank you.
Okay.
Thank you. And there's another question from Professor Zhichen. He said, it seems that the supercritical effects do not have a major role on the flame chemistry. We have seen similar results in other recent talks. How do we interpret this from a physical perspective?
Yeah, that is actually easy to understand, because if you look at the thermodynamics, you can see that looking at the phase diagram. Typically, if temperature is larger than 3 times the critical temperature, or if the pressure is larger than 2 to 3 times, well, mainly the temperature. If the temperature is larger than 3 times the critical temperature, then ideal gas is always a good assumption. If you now look at our flamelet results, let's go down to the flamelet. We can see that the temperature is rising very fast. So again, this is a logarithmic scale. So basically, where you have combustion, the temperature is like 100 times the critical temperature. And that's not true. It's like 10 times the critical temperature. That means that where there is chemical reaction, or like where there is combustion, real gas will not have an effect, at least not with hydrocarbons or with the fluids we usually burn. And that is the explanation, that inside of the flame, it's basically still mixtures of ideal gases with non-constant Cp, but the enthalpy is not dependent on pressure, but the mixing, where you have inert cold mixing, there the real gas effects will be important. So there's an interesting discussion in these flames, usually in this coaxial injector flames. The flame is stabilizing here directly on the post. So that means the flame is sort of directly outside of the cold jet. So the mixing is already taking place, or a lot of the mixing is taking place at higher temperatures, and then the real gas effects just go away. Does that answer the question?
Professor Zhichen?
Yeah.
Yes, he said yes in the chat.
Ah, very good.
Okay.
Okay.
Okay, is there any more questions from the audience?
Can I ask one more question?
Sure.
Yeah. So on page 11, you mentioned the sequence of updating the thermodynamics within the simple loop, right? Pimple loop. So
yeah.
So in this simulation, actually, does the sequence, I mean, outside or inside the loop, is this important, for this simulation?
Yeah, for this simulation, we found that at least you have to put the enthalpy inside. You have to keep the enthalpy constant, and you have to recalculate the thermodynamics inside the loop. We have not tried to do the loop around all the equations.
Okay.
So there are some numerical algorithms which use this blockwise iteration, where you solve all the transport equations in one step.
Okay. Yeah. After
but we are not doing that.
Yeah. After this is a segregated method, right?
Yeah. Yeah. We are using the segregated method, but we found that it is important to calculate the thermodynamics inside the loop with constant enthalpy and not with constant temperature.
Okay, but how about the density? Because density actually is updated outside the loop, right?
Yeah. But density is taken into account inside the loop through the thermodynamics.
Okay.
So the pressure loop calculates the pressure, but then the correction is done using the real gas density. That's what this this loop here means. Where is it? So here. So
Yes.
that means that the pressure equation, this thermodynamics will then recalculate the density using the pressure and using the enthalpy which is outside of the loop.
Okay.
So, but still continuity, momentum, enthalpy, and the turbulence and the species is done sequentially.
Okay. Yeah. Okay. Okay. Yeah. Thanks. Thank you.
But it may actually be more efficient to use a block structure. We have not tried.
Okay. Yeah. Okay. Thank you. Yeah.
Is there any more questions? Okay, no more questions. I would like to thank Professor Pfitzner again. Yeah.
Oh, one more question from.
One more question from Professor Zhichen. There's a transonic mode for pistol in OpenFOAM, where the compressivity factor psi is updated iteratively.
Okay, as in the transonic or supersonic simulations, as I said, we use this hybrid simulation with the Kuganov-Tadmor. Actually, in our loop, we use a different the compressibility factor psi. This is modified. This is modified because it's different for real gas than for ideal gas. And I'm not sure. I think the compressibility factor is updated iteratively inside the loop. And it's modified because it has to take into account that enthalpy and temperature are not proportional to each other anymore. But there you would have to look into our papers. I don't have a foil for that.
Okay. Thank you. I think no more questions from the audience. So I think our time is up. I would like to thank Professor Pfitzner again for this very wonderful and insightful talk. And I would also like to thank you all for attending this week's webinar. And thank you and goodbye.
Okay. Thank you.
Okay.
Yeah. Thank you.
Thank you.
Yeah.
Thank you. Bye-bye.
Thank you. Bye-bye. Bye-bye.